Hey guys, Mr. Mac here. Today I'm going to do the second part of 3.5 transformations of functions. And in this section we're going to look at stretch and compression. So the first thing we're going to do here is we're going to talk about vertical stretch and compression. So when we multiply a function by a positive constant, or a constant is a number like 2, 3, -1, we get a function whose graph is stretched or compressed vertically in relation to the graph of the original function. Okay, so let's take a look at f of x equals x squared. And I hope by now you guys have a strong handle on what this graph looks like, because we've been doing a bunch of these already. So I know I've got 0, 0, I've got 1, 1, 2, right? 2 squared is 4, so I got 2, 4. And then I've got the -1 squared would be +1, -2 squared would be +4. And so here is our parent function. And now we're going to see what happens when we multiply the function by a constant of 2. Okay, so let's do this in red. So if I multiply this by 2, I'm going to execute everything inside of the function here just like I did, and then I'm going to multiply whatever that result is by 2. So I already know what f of x is because I just got a whole table of values already here. So this is just going to be 2 times whatever these original outputs are. So it's going to be 2 times 4 is 8, 2 times 1 is 2, 2 times 0 is 0, 2 times 1 is 2, 2 times 4 is 8. That's an 8. Okay, so now I've got 0, 0, 1, 2, 2, 8, -2, 8, and then we have this graph. Now you will see that it has been stretched vertically by a factor of 2. So all of these points here on the outputs have doubled from the parent function to 2 times the parent function. Okay, so what happens when we multiply by a constant that is less than 1, or between 0 and 1, like 1/2? So that's just going to take all the original outputs that we had here from our f of x, and it's going to halve those outputs. So instead of 4, it's going to be 2. Instead of 1, it's going to be 1/2. 0 times 1/2 is still 0, and we got 1/2 and 2. Okay, so I got 0. Okay, I'm going over 1, 1/2. I'm going over 2, 2. -1, 1/2. -2, 2. And here is my function graph. Okay, so it got compressed along the vertical axis. So it got squeezed vertically. Okay, so maybe I'll just scroll down here. So we see that if we are multiplying a constant here on the outside of the function, this is going to affect the vertical stretch or compression. If a is greater than 1, then it'll be stretched like it was here when a was 2 in this case. So it stretched it vertically. If a was between 0 and 1, then the graph is going to get compressed, like we saw 1/2 right here on the green graph. It got compressed. If a is less than 0, it means it's negative, so that actually causes a reflection. So the reflection too can be stretched or compressed depending on those values. Example 13, using our OpenStax book here. So let's say we have a function p of t that models the population of fruit flies. So this is the population of fruit flies right here. Okay, that's the y-axis. And t is going to be it's going to be time, right? Scientists are comparing this population to another, but is twice as large. So this is going to be time Doesn't say what it is. It could be minutes, days. Fruit fly is probably days, right? So a scientist is comparing this population. Okay, so this population, it starts at 1 at time 0, and then it goes up at 3. It goes to 3 at time 3, and then starts to decline to 6, and then at time 7, it's 0. So there is no population. So we're looking for a new population, Q of t here. And Q of t, it says right here, is going to be twice whatever the P of t is. Okay, so what are we doing here? We're multiplying this by a constant, and this constant a is greater than 1, so it's going to cause a stretch, just like we saw right here when we multiplied f of x by 2. It's going to stretch along the vertical axis. So we are going to double the outputs that we see here for any of the original P of t. So if this is at 1, we're going to double that to 2. Right here, this one is at 3. We're going to double that to 6. This output right here at time 6 was at 2. We're going to double that to 4. And then right here at 0, with double 0, it's just 0. And now I'm just going to try to fit this curve in at these points. And there is our graph. Okay, so this is Q of t. And this original one right here was P of t, right? Okay, very good. Find a vertical compression of a tabular function, so a function that is written in a table. A function f is given right here, so we have our inputs x, and here are outputs f of x. Create a table for the function g of x is 1/2 of f of x. Okay, so at 2, my output was 1. So what are we doing to the 1 here? We're multiplying it by 1/2. So my g of x here is going to be 1 over 2. My output here for 4 was 3. So I'm going to take the 3 right here and multiply it by 1/2. This would just be 3/2. 6 is 7. My output is 7. So I multiply by 1/2 is 7/2. I'm just multiplying by everything by the same constant of 1/2. And that's all we need to do. So maybe I'll take it one step further here. Let's say I have this graph right here, and I've got 1, 2, and so our output is 1, and then I've got 3, 1, 2, 3, 4. I'm just plotting, this first table right here. This is f of x, 6, 3, 4, 5, 6. I'm up to 7, 4, 5, 6, 7, something like this. And then at 8, I'm at 11, 7, 8, 9, 10, 11. I'm up here. And so maybe this graph would maybe kind of do something like this. I don't know. I don't know if it's continuous or not. So here are my points. And then this one right here is going to get compressed. I'm taking half of all of these. So instead of 2, 1, it's going to be 2, 1/2. So it's half of that distance from the axis. Instead of 3, it's 3/2. 3/2. 7/2. It's just going to be half this distance. 11/2. Something like this, right? So this graph's going to look like this. Everything is just getting compressed because the constant is 1/2. Okay, recognizing vertical stretch. So now I'm giving you a graph, and we recognize that this is a function x cubed. And we know why don't we graph this function x cubed? We know what it looks like, right? It starts at 0, 0, and we put 1 in. 1 to the third power is 1, 1, 1. If we put in -1 in here, we would get -1. Remember this S-curve? And then 2, 8, right? 2 cubed is 8. 2, we're all the way up here. 6, 7, 8. It's all the way up here. And if I put -2, I get -8. We're all the way down here. So it's going to look something like this, right? So what's happening with this function that we're given? Do you see that it is being compressed? So that means we're multiplying by some sort of fraction to reduce my outputs. So what is it reducing by? We know this point right here, we see this point is 2, 2. But we know in the parent function that this would be up here, would be at 2, 8, right? And we know this one down here would be at -2, -8. But when we look at this position here, it's at -2, -2. So how are we going from -8 to -2 and 8 to 2? Well, we're multiplying by a quarter, aren't we? Like 1/4 times 8 is 2. If we look at this right here, I zoom in, so this is at 1, 1. This right here looks like a quarter, right? If we were to divide this up into quarters, this looks like 1 and 1/4. So looks to me that our constant for this problem, and we're calling this g of x, so g of x is going to be 1/4 x cubed. All right, there is our new function and our new formula for g of x. Okay, horizontal stretches and compressions. So this next section, I always start off with vertical because it's a little more straightforward. When we do the horizontal, we have to kind of think a little bit more how this relationship is going to be a reciprocal relationship. So we just have to think a little bit more and try to bend our minds around how this works. We already talked about f of x equals x squared. We already know these values because we've been working with them for a while. So we got this parabola again going through these points that we've firmly established for our x squared function, like this, okay? Now, we are going to put the constant inside of this function now. All right, so it's going to be, it's not outside, it's not 2 times f of x, it's f of 2x. So this is going to affect what our inputs are going to behave within the function itself. So what's happening here is we're saying g of x equals 2x, this whole quantity, squared, okay? So when I put in 0 here, let's try this, 0 in here, I still get 0, 0, 0. When I put 1 in here, okay, 1, sorry, I'm putting in 1 here, and I'll write it there. 2 times 1 is 2, and then I'm going to square that. So 2, this would be 4. And then I'm going to put 2 in here. 2 times 2 is 4. 4 squared is 16. And I'm going to get the same mirrored on this side. -1, 2 times -1 is -2. -2 squared is 4. And then this one also give us 16. So this is going to be, do this in red maybe. So 0, 0, 4. Sorry, 1, we're going over 1, 4. -1, 4. And then 2, 16. I'm way off up here. Okay, it is very quickly going off the graph. So I'm trying to make this a curve here. This is not a straight line, and it's going to go very quickly that way. Okay, so in first inspection, you would think, oh, this is being stretched vertically. But really, because it's happening inside the function, and we know that when we dealt with other kinds of graphs where we were doing transformations, like x plus 2 squared, remember when we did this? Anything that was inside the function like this translated the graph left to right. So this time it's moving it left, right, if I were to do that one. So if we're multiplying inside by something, that's going to affect it going horizontally. So really what's happening here with this is we are compressing. This one's compressing the graph when we're multiplying by 2. Okay, it's a horizontal compression. Now, this one we're going to use a constant of 1/2. So what do you think is going to happen with this? So if I put in 0, 0, we still get 0. So I get this point right here, still 0, 0. Now I'm going to put 1/2 in here. So now I've got a g, sorry, we're on h now. So this is h of x equals 1/2 x squared. So when I put 1 in here, 1/2 times 1 is a half, and I square 1/2, I get 1/4. So negative 1, it would still give me a positive fourth, right? So now I've got 1 1/4, so I'm way down, right, it's kind of close to the x-axis here, quarter. And then I'm going to put 2 in. So 1/2 times 2 is 1, and I square that, I get 1. So I've got 2, 1, negative 2, 1. All right, so here we got this right here, this graph, something like this. And this one is being stretched horizontally. So this one's horizontal stretch. Okay. So here are our rules. Given a function f of x, a new function g of f of bx, where b is a constant, if b is greater than 1, like it was here when it was 2, it will be compressed by 1 over b. So this one got compressed by, so you see we're taking the reciprocal here, so the b is greater than 1 here, so it's 2. It's going to be compressed by 1 over 2. So that means anywhere where we had a point like this right here, it was 2, this is the original, our input would be half of that. So now see we went to 1. So we took half of that input to get the same output position. Conversely, if b is a fraction between 0 and 1, then it's going to be stretched by 1 over b. So our fraction is 1/2. So in this case right here, I'm saying, okay, 1 over 1/2, right? Because b is a half. And we know that, if we multiply 2 top and bottom, this will be 2. So really we are doubling this stretch here. So the green is being doubled. So when we were originally here at an x value of 1, it's being doubled this way to an x value of 2. So we've doubled the x input for the same y output position. Okay? So we just have to think about, in slightly different terms, when we are multiplying by a constant on the inside of the function, whereas the vertical stretch, we're multiplying the function on the outside, like we saw with these examples here. Okay, let's take a look at 16. We're going to do a horizontal compression here. So back to the same fruit flies that we saw before. We're saying now, suppose a scientist is comparing a population of fruit flies to a population that progresses through its lifespan twice as fast. So remember, this x right here was time, right? So time being lifespan. I don't know if it's days. It looks like hours right here, right? Looks like hours. And this new population, R, will progress in 1 hour the same as the original does in 2. Okay, so our population, the fruit flies don't live as long. They live it looks like half as long, right? Okay, so we're going to start off with the original population of 1 right here. Do this in red, boom, okay? But now, 3 hours is going to be accelerated with this R of t population, and it's going to be half as much. So instead of 3, it's going to be 3/2, or 1.5. Okay, it's going to be the same output here. So this one right here was 3. Now this one here is 3/2. Okay, so now that's going to go like this, that curve. And then this one right here, my x value, my time value here is 6. That's going to get cut in half to 3. So right here we have a 6-2 position. We're going to get a 3-2 right here. That is a time of 3. So then that's going to go down like that. And then 7, instead of a original time of 7, we're going to have that. So half of 7 is 3.5 right there. And this is going to come down in right there. So you see we have compressed this graph horizontally by having all of the input values and match the exact same output. Okay, let's take a look at a tabular. What do we have here? We got a few more. Find a horizontal stretch for tabular function. So function that is written into a table. So here's the original right here. We've got 2, 4, 6, 8 are x values. We got 2, 4, 6, and 8. And here are outputs 1, 3, 7, 11, and they're plotted right here in this graph. Okay, I think I added this. I don't think that's in your notes. Now we're going to make a table for g of x. Now what's happening inside here? We are having all of these values. So I think I'm going to fix this right here. I really wanted to add an extra column. So really, we're having all of these original ones here. So we're still going to have 2, 4, 6, 8 here, right? But what are we putting into the x in order to get this, right? I mean, I'm going to put a value in, it's going to have it, and I'm going to still get the same output. So I'm going to extend this over here, this, just adding an extra table, row, and this is going to be x. So what are we going to put in for x to get something times this input times 1/2 is going to give me 2. So doesn't this need to be 4? Right? Now, just think about this. I'm stretching. This 1/2 is going to stretch, right? It's going to stretch horizontally. I'm going to have to push away from 0 here. So I'm going to have to double all of these in order to get these original inputs with the function. So if in order to get 4, I got to put 8 in there. 8 times 1/2 would be 4. 12 times 1/2 would be 6. 16 times 1/2 would be 8. And so if we come over here now, we say, okay, so I've got, I'm going to put in 4, 1. So if it's going to come out over here, 4, 1, 8, 3, 12 matches with 7, 12, 7, and then 16, 11, right here. So do you see all these points are getting stretched this way by a factor of 2. We're multiplying all these x positions by 2. Okay? Now I've got another table here. It says recognize horizontal compression. Okay, so we're relating the function g of x to f of x. So what is happening to f of x to get g of x? So this point right here is going there. This point right here is going here. And of course 0 is still at 0. So I'm going from an output here of 6. So my x value here is 6. And then my x value right here is 2. So what do I do to 6 to make it a 2? What do we multiply 6 to get to 2? This one right here looks like we're at 4 on the x. And then right here it looks like we're at like 1.3 or something like that. So what's happening here? We're going from 4 to 1.3. What are we multiplying through here? It looks to me that we are multiplying these values by a third. Right, so 1/3 times 6 is 2, and 4 times a third, right, is going to be 1 1/3. So that looks like 1 1/3 to me. So we are compressing here by a factor of 1/3. Now what happens, let's go back to here. What's the actual value going to be when we are compressing by 1/3? What's our b value going to be? Well, we're going to have to take the reciprocal of it, right? We're going to have to take the reciprocal of the b value. So our b value is going to be 1 over 1/3, which is 3. Okay, so the b value is greater than 1. It's going to, let's just check that right up here. Let's look. Right here, when our b value was a value that was greater than 1, like this right here, this red graph, you see how it compressed it horizontally? And that's the situation that's happening right here. This graph, going from the blue to this brown right here, is being compressed. So my new function here for g of x is going to be f what's happening to f to get the g? We're compressing it so that we go 3 times x. This is a factor here of 1/3 because we take the reciprocal. Okay, that one is done. Example 19, the graph of f of x is the absolute value of x is vertically compressed by a factor of 1/3. Okay, vertically compressed. So vertically means that we are going to take our constant and multiply it on the outside of our function. Okay, it's going to go outside. It's getting shifted to the right. Okay, so that means we're going to have to subtract inside the function here. So let's say maybe I take that off. So we're going to have to subtract 3 inside there, and it's moving up 2. Okay, so let's see if we can write this. F of x equals, we are compressing a factor of 1/3. It's opening up, so it's not negative, and it's an absolute value function. We're going right 3 units, so we're going to subtract 3, and it's going up 2. Okay, there's our equation. That's it. Describe how the equation is transformed and graph it. Okay, so a is 2 right here. This is going to be a vertical stretch. We've got a horizontal shift. It's going right 4. Okay, because this is a part right here. And then plus 2 is a vertical shift. We're going up 2 units. Okay, so absolute value, we know what absolute value looks like, right? So absolute value looks like this. Okay, so we are moving all these points here. I'm going to move it right 4 and then up 2. Okay, so right 4 and up 2. So if I were to do the next graph, I could do this. Okay, so I'm just showing the shifts here. Now we need to do the stretching. So what's going to happen when we multiply by 2? It's going to increase the output double to the original. So instead of going up 1 like it does here, it's going to go up 2. So it's going to go here. And this one right here, instead of going up 2, it's going to go up 4. Okay, so it's going to cause, really another way to look at it is that the slope here, instead of being 1/1, it's going to be 2/1. So we've doubled the slope of this line. Okay, and there it is. This right here is our new function, f of x. Okay, so we added that one extra piece here in this section where we're multiplying by a constant either outside the function or inside, and it just affects the vertical stretch or compression or the horizontal stretch and compression. And that is the last piece for being able to graph any type of function. Okay guys, hope that makes sense, and I'll check you later.